if you could share your slide, because you're the first presenter. Okay, excellent. So I propose we start. Kieran, is this okay to start?
Yes, please. Thank you.
Okay. Okay, thank you. So let me introduce the first speaker, and welcome to all of you for joining us in this last session of the NIPAA workshop. So the presenter, Haoyu Zhang, is a senior principal network architect at Futurewei Technology. He received his doctoral degree in computer science engineering from Washington University in St. Louis. Before joining Futurewei, he was a researcher with Bell Labs Alcatel-Lucent, and his research interests include programmable networks, network data plane algorithms, architectures, and protocols. So, dear Haoyu, the floor is yours.
Thank you for the introduction. Can everybody hear me? Okay, so today I'm going to present this adaptive address for next generation IP protocol in hierarchical networks. This is a joint work with Zhaobo, Zhang, Yingzhen, and James Guichard. We have entered the 5G era, and IoT is prevalent. Which will introduce billions of internet addressable entities into the internet. And IPv4 addresses has been used up, and the transition to IPv6 is inevitable. However, IPv6 has a very big packet header overhead. We all know that. And the first thing is, it's ill-suited for IoT networks. For example, in IoT networks, most communication involve very short messages. They are energy sensitive, delay sensitive, and also the resource limit has a resource limit, which all renders a large header overhead unfavorable. In IPv6, the address field alone will consume 80% of the entire layer 3 header. And that's another issue because IPv4 and IPv6 are both fixed-sized address scheme. And so it makes the address extension very difficult. What if in the future we need another parallel address space alongside of IPv6? What if in the future when we evolve into another address scheme, we still want to keep the old address unchanged? So that's both very difficult for IPv6. So that's why we need something new. And here's some key observations. In the today's internet, actually, oh, sorry, let's go back to the next slides. We believe there's a practical solution to these issues. So this is based on some basic observations. The IoT networks and the data center networks naturally follow a hierarchical network architecture. In IoT networks, edge device communication directly in the local networks. So the edge, also most of the communication tend to be limited to the local area only when the local area cannot satisfy the communication requirement. It will use a remote data center as a last resort. Similar thing happens in the data center network, where the east-west traffic is dominant. And also the communication involve a lot of short message, key value pair exchange. And based on this type of traffic pattern, a user tends to limit the communication within a single rack or even single pod and in single data center. So let's see how we can take advantage of these observations to make the entity to retain the minimum address information. So in a hierarchical network, an entity address actually can be divided into two parts. It's network ID part and entity ID part. So the entity ID can uniquely identify entities in a local network. And we delegate the maintenance and operation of the network ID to the networks. So each entity only needs to know its own entity ID. So for communication, of course, it needs to know the peer address, peer's address, which include the part of a network ID if it's in another network. But if both of them in the same local network, they can only use their entity ID for communication. Since we have a multiple level of networks, so the network ID can be also partitioned into multiple levels. And each level of the network only maintain its own section of the network ID. Using this idea, we can significantly reduce the overhead, address overhead. So let's use an example to illustrate the idea. Assume we have such a mail delivery system, which include multiple hierarchical levels, which are city level, state level, and country level. So if so all the users in this system only need to know its own street address. So if two users are in the same city, for them to send a mail to each other, they can only use their own street address. However, if in another example, if the two users are in the different city and different state, but in the same country, more interesting will happen. Again, this time, the user, if it wants to send a mail to another user in another state, it only uses its own street address as its source address. But this time, it needs to know the destination, the user's state and the city, and its user is a full address as a destination. So it will send this email, this letter to the city office. So and the city office, interesting thing happens because this city office know this mail will go to another state or another will be delivered out of this city. So it will add its city name to the source address. Then this mail will be delivered to the state office. Then at the state office, it will add the state name to the source address. Now the source address and destination address at the same level, so it will no longer be delivered to the country border office, but it just delivered within the country and go to another state. And the destination state, the state will remove the state name from its destination address and forward it to the city office, and the city office will further remove the city name from the destination address. So finally, the receiver, when the receiver receives this mail, okay, it has the full address of the source, but it has only its own street address as a destination address. So to support this in internet, we need to modify the IP header. So the new header will include a source address length field and the destination address length field, followed by two variable sized source address and the destination address. And in our network, each level network has one or more border routers. We call them level gateway routers. So these routers are responsible for forwarding packets in and out of the network. So the LGR will keep a unique prefix for the network below it. And because this prefix is a network ID, then for each egress packet, LGR will add a prefix to the source address. And for each ingress packet, it will remove the prefix from the destination address. So this is just some very simple operations. And within each level network, there's another type of router. We call that ILR, or inter-level router, which are responsible for forwarding packets within the network. So in those routers, they will not touch the address fields. So one great thing about this scheme is that it can seamlessly work with existing IPv4 and IPv6 networks. We assume the new version of is IPvN, and we have two possibilities. The first one is to make the entire IPv4 and IPv6-based internet today as the lowest level network within the IPvN domain. So then we can have the entire IPvN-based network hierarchy alongside of today's internet. The second option allows us to grow the IPvN network within today's internet. Here we can further have two sub-options. So the first option is we can reserve some IPv4 or IPv6 address blocks for IPvN networks. Then each top-level IPvN network will have a private address space, and it uses network address translation to communicate with the IPv4 or IPv6 networks. Or we can have a more interesting scenario. Here we just reserve an entire IPv6 address blocks. So essentially, each top-level IPvN networks will own a sub-address space. So in this case, the border router between the IPvN and the IPv6 is slightly different. We name this a special router IPT, called the IP Protocol Translator, because it will also responsible for conducting the protocol header conversion. We believe this is the most compelling scenario to introduce this new address scheme to the internet. To make it work, almost all the control plane protocols in IPvN networks need to be changed. However, we found they are all become more simpler, thanks to the strict hierarchical network architecture. Here are some examples. In each level of network, there's a DHCP server who is responsible for assigning ID for entities in this network. Each level of network also has a DNS server to provide the domain name service. Due to the hierarchical network architecture, all the DNS servers forms a tree structure. A name is resolved from a tree node toward the tree root until the name is found. And the architecture naturally supports name scoping and name overriding. And the ARP protocol is also very similar to that for IPv4 and IPv6. In particular, the LGR serves as ARP proxy for its prefix or network ID. As for the most important routing protocols, a lower level network can be considered as a single AS. So today's IGP protocols like OSPF and SS can be modified to run it very easily. The higher level network can contain multiple AS, in which the lower level networks are stub AS. Due to the time limits, we won't talk about details about this. You can find more details in our paper. For the data plane, the end entity network sockets need to be extended to support a new layer 3 protocol. However, all the other layer of protocols below and above L3 are unchanged. The new L3 protocol header should be designed to be able to convert to IPv4 and IPv6 without any information loss. For the router, due to the network architecture, there will be no nested prefix in the forwarding table. And due to the network level address aggregation, we can envision the forwarding table will be very small compared to today's forwarding table. And the new functions introduced by LGR and IPT can be easily supported by hardware. We use P4 language to prototype the data plane implementation and use BMV2 for simulation and emulation. We design an IPv4 header format using the version number of 8. So this header can be directly translated into an equivalent IPv4 or IPv6 header if a prefix is given. The network including routers and hosts run in Mininet. So the entire simulation environment is built as a Docker container. Currently, P4 doesn't support the variable length header field very well. So we tried two approaches for the IPv4 address parsing. We found the second approach is faster and it's also less flexible. We hope in the future P4 can be improved to support the variable length header processing better. Using this simulation environment, we first evaluate the packet processing performance for different routers in IPv4. Note that since the entire experiments run in a container, here we only mean to examine the relative performance for different scenarios. Also, we use a very small forwarding table, so the table lookup cost is negligible. And here the performance is mainly determined by header processing. In the first experiments, we examine the per packet processing time for different type of routers. We can see LGR is the most time consuming because it needs to modify the address field. In the second experiment, we compare the packet processing for IPv4, IPv6, and IPv4 packets respectively. Although IPv4 could be 30% more time consuming than others, we claim the hardware implementation can eliminate the header processing difference. And because of the smaller and simpler forwarding table, it will make the IPv4 actually outperform the routers for IPv4 and IPv6 processing. Next, we compare the IPv4 overhead with the IPv4 and IPv6. If we only look at the address part, IPv6 needs 32 bytes and IPv4 needs 8 bytes. For IPv4, the bytes needed will increase as the network size increases. When the network size is 3 bytes, IPv4's address field becomes the same as IPv4. However, in this case, the network can contain up to 16 million entities. So in reality, we rarely need such a big network. So in any case, compared to IPv6, the saving is significant. If we consider the entire L3 header, IPv6 needs 40 bytes and IPv4 needs 20 bytes. When if we, for IPv4, only need 12 bytes for a network with a reasonable size. Also, based on these results in the wireless IoT environment, when the packet size is moderate between 16 to 128 bytes, when using IPv4, we can save up to 20% to 50% of power. So conclusion, in this talk, we introduce an efficient addressing scheme for IoT and data center networks. Meanwhile, the scheme supports future address space extension without needing to touch the existing network and entities. The best feature about it is that it supports incremental deployment from the edge. We don't need even to standardize it because we can make the entire edge network totally oblivious to the external network. It's fully interoperable with existing IPv4 and IPv6 networks and entities, which means an IPv4 entity can communicate with existing IPv4 and IPv6 hosts without any problem. We open source this our prototype and also published an extended version of the paper on the website, which include more details on the website. We hope this work can trigger more interest and discussions from the community. Thank you very much.
Thank you very much. Haoyu, for the very interesting presentation. Thank you very much. Let me check if there are questions on the Q&A parts in Hoover. Yeah, there are no questions yet, but feel free to put your questions there, or feel free to use your microphone or share your camera to ask a question to Haoyu. And in the meantime, I have a question. So the main focus is on IoT, Industry 4.0 kind of applications. And then the latency for particular applications can be important. And then the question is, how much can your technique, or to what extent can we reduce latencies? And did you evaluate which percentage of latency reduction that you receive for typical scenarios?
We didn't evaluate the latency latency but the point is at the edge network, they will directly communicate with their only entity ID, which is a very short compared to the full address. So the time involved for header processing will be shortened in the edge network. So yeah, conceivably, it might save some latency. But the more important is save the bandwidth, also save the other resource like power.
Yeah. But for some applications, latency is really critical.
Yes.
And then it would be interesting to know: are we talking about a reduction of 5%, 10%, 20%? This would be interesting to know.
Well, without a real hardware implementation, we really can, because now we only have a software emulation. In software, the performance is very poor because it's slow. But in the hardware, only when we have a real hardware implementation, we can do a true real evaluation for the performance gain. But we expect there will be some gain at least for the latency.
Yes, for sure, there will be gain. But it will be interesting to characterize this. Yeah. Okay, thank you very much. Let me have a look if there are other questions. Are there other questions from? Yes, please.
Thanks, Haoyu. Very good. So this looks very similar in concept to E164 and how we're dialing shorter or longer phone numbers, right? I was just wondering, maybe I missed that bit of detail, but in E164 there are specific, indicators that let us know, how many prefixes we include, right? Like the area code or the country or something. How is that in your proposal? Is that derived from the length of the address, or do you have other indicators to know how many prefixes are in the address?
So the point here is that the entity itself doesn't need to know anything else but its own entity, entity ID. So that's for sure. It also includes the length of this entity ID. But beyond that, so every level of a prefix only owned or maintained by the border routers. So if we can realize this, then actually you have no limits to extend your address length. The information kept by the entities is minimum. Which means we just hand off the address manipulation to the border routers while keeps the entities as simple as possible. So that's a whole idea about it. So I'm not sure if I answered your question clearly, but that's a basic idea.
Well, I mean, I think the question is about the ambiguity of addresses that was avoided by having these, selectors in E164 addresses. If I'm going to have to address an entity that is remote, then I need to use all the prefixes to address it. And so then the question is, what's the logic by which I'm figuring out whether or not for an entity for which I know the full address with all the prefixes, I can abbreviate. right? And
okay. So if your destination entity is in another network, you will need to use a DNS service to get its address. But the address return will be just as long as the lowest level common networks they shared. So they will not give you a longer address than that. For example, if in my illustration example, if they are both in the same state, then but in a different city, you will get the destination address back just up to the state level. It will not include the state ID to the address. So in this case, there's no ambiguity. The router will exactly know where to forward your packet.
So this is the approach used in older net implementation that are relying that all the address lookup are done through the DNS system, and you're never carrying addresses explicitly in protocols.
Yes, probably.
Okay, thank you.
Okay, thank you for the question. So with this, I believe we have to close this presentation and Q&A section. Thank you very much.
Thank you.
Haoyu, for the interesting presentation. We now move to the next presenter, which is Xiao Zhang. So
Yeah.
Xiao, can you please share your slides? Thank you.
Thank you. So can you see my screen?
Yes, it's in design mode. Yeah, now it's presenter mode.
Okay.
I will very briefly introduce you. Let me pull up your CV here. Okay, here I have it. So Xiao Zhang is a second-year PhD student at Computer Science and Engineering department at Michigan State University. His advisor is Dr. Xiao, who is the second author of the paper. And the presenter, the author, currently focuses on next generation communication and networks, especially optical wireless communication, including millimeter wave networking, mobile computing, and Internet of Things. So, Xiao, the floor is yours. Thank you.
Okay. Thanks for the introduction of Dr. Filip and the organization of Kira. So I will start. Hello everyone, my name is Zhang. Today I will talk about one of the NIPAA techniques, optical wireless communication, short as OCC. We are from the Computer Science and Engineering Department at Michigan State University. Our work is named RainbowRow, Fast Optical Camera Communication. I will divide today's presentation into 5 sections. Firstly, introduce the background of optical camera communication. Secondly, I will present some OCC concepts and preliminaries. Thirdly, I will explain the design of RainbowRow and its principle. Then evaluate RainbowRow's performance. Finally, report the conclusion. So new high-speed multimedia applications and massive Internet of Things, IoT services, such as the immersive entertainment, autonomous manufacturing, transportation, smart home, and retail in the future services continue to emerge with higher requirements. Existing popular wireless infrastructure such as Wi-Fi, Bluetooth, and LTE are based on radio frequency, RF. However, even potential higher RF bandwidth, such as millimeter wave, is soon no longer sufficient for future massive high-speed wireless services. While the optical wireless spectrum has more than 10,000 times broader bandwidth, light-emitting diodes LED with fast switching property make it possible for high-speed optical wireless communication, which is short as the OWC. So OWC technique include Li-Fi, OCC, VLC, FSO, and etc. Optical camera communication is short as OCC, It is one of the technique of OWC. OCC has attracted more attention due to its low interference, low price, and the smartphone's popularity with built-in cameras. However, developing a high-speed, low-cost, and practical CC system is still an open issue. I will introduce three basic OCC concepts and preliminaries. They are amplitude diversity, spectrum diversity, and spatial diversity separately. Firstly is the amplitude diversity. Amplitude diversity means the grayscale difference. We can use the PD, which is the photodiode, or PR, photoresistance, to measure the grayscale value. That is to see the intensity of the light emitting or reflecting from the light source or the objects. Different amount of light can be reflected as a different voltage or digital signals in the circuits. Red, green, and blue are combined in various ways to reproduce other colors. This is called the RGB color model. In the IEEE standard, it defines the color shift keying CSK modulation. The optical symbols are generated based on the points on the CSK constellation triangles. Compared with the RGB model used for color generation, the HSL model is more natural to describe the colors and the more popular for color recognition at the receiver for color detection. H stands for the hue, which corresponding to the red, orange, yellow, green, etc. The HS hue reflects the changes of the difference of the colors more directly. So this is the second diversity, spectrum diversity. HSL model separates the brightness and the color of the light, which are the amplitude diversity and the spectrum diversity separately. So this is the second diversity. The third diversity is a spatial diversity. It is a new insight. The shutter is a mechanism of camera to control the effective exposure time of a photographic film. There are two kinds of shutters, global shutter and the rolling shutter. A global shutter exposes the whole thing at the same time. Light sensors at each pixel collect light synchronously and are exposed simultaneously to form an image like this. Rolling shutter is implemented by exposing one row of the pixel simultaneously and in a row-by-row method to generate a whole photo. Thus, the rolling shutter has a higher readout frequency than the global shutter. Existing rolling shutter-based modulation methods, for example, CUSC measures the average grayscale of each of the pixels from one strip or the row and decode it as a symbol. However, each row comprises multiple pixels and could record the multiple colors or the grayscales in different parts of pixels in this row. So this spatial diversity on each row provides the possibility to boost the throughput further. Based on the analysis and principle in last section, we propose combining amplitude diversity, spectrum diversity, and the spatial diversity to improve the OCC system's data rate. Due to each row will be colorful rows, so we named the protocol as the RainbowRow. Diversity combination can eliminate the short symbol distance limitations for each diversity. We can employ the robust and proper range in each diversity for modulation separately. Let A denotes the amplitude diversity, as 1 denotes the spectrum diversity, as 2 denotes the spatial diversity in each row. The bits denoted in each symbol can be represented as this formulation. For instance, if we adopt 4 levels of grayscale and 4 different colors and at 4 different locations as the transmitter, this combination can output a total of 16 bits per symbol. It is faster and more robust without the limitation of short symbol distance in each diversity. Our proposed RainbowRow modulates optical signals with a combination of lightness, color, and location. For example, the transmitter have 4 locations. In each location, it can generate 4 colors with 4 different brightness level, as shown in Table 1. So about the RainbowRow system implementation, it includes 2 parts. One is the low-cost LED-based transmitter design. The second part is the real-time camera-based receiver design. So for the transmitter design, we use the commercial LEDs as the OCC transmitter. To generate multiple colors, we adopt a tree LED instead of the single color LED for the spectrum diversity. The transmitter should be composed of the multiple tree LEDs for the spatial diversity, synchronously controlled by the driver, and deployed at the proper position. OCC transmitter have 2 functions, so we adopt the this LED panel with the 3 colors. Also, the OCC transmitter have 2 functions. One is the communication, and the other important function is lighting. Thus, the communication process should offer constant and smooth lighting. However, some specific optical symbols appears in low frequency due to the probability of its presented bits. These optical signals will cause flicker. We mitigate this flicker by rescheduling the coding table to increase the probability of different colors appearing in 4 blocks simultaneously. So about the receiver side, although the HSL model is better than the RGB model for color and amplitude detection, it still faces the color distortion and is impacted by ambient light. The receiver decides the H and L threshold dynamically based on the measurement will preamble optical symbols. As for detecting the optical signals spatial location, we deploy and hold the camera pointing at the LED panel. We also need to select a region of interest, ROI. Different sizes and locations of ROI will influence the symbol detection accuracy. The best location of ROI should have the same horizontal center with the related blocks of LED panel. Besides, different rolling shutter frequency will generate strips with different strip width. Thus, the ROI should have the same or less height of the strip width. So this is our design and the solutions. In this section, we conduct experiments to evaluate the performance of the RainbowRow. We adopt an 8x32 WS2012B LED panel controlled by Arduino Uno. As the transmitter, use a commercial web camera connected with the PC LabVIEW program as the receiver. The bits will be split into the bit sequences and then will be mapped into different combination optical symbols based on the symbol coding table. Transmitter then generates the optical signals with 3 diversity. The receiver then captures the image via a camera and demodulate symbols into bits. Finally, the bits sequences will reconnect into the bit streams. RainbowRow modulation can ideally achieve a faster transmission rate through the combination of optical signal diversity, especially the utilization of the spatial diversity. Nevertheless, its actual communication performance also depends on the symbol detection performance. In our diversity combination, spatial diversity is the most reliable due to the relatively fixed transmitter and receiver. The testbed can match the locations with optical symbols correctly. As for the spectrum and amplitude diversity, they are more related to the optical environment. We evaluate these two diversities reliability by adjusting the transmission frequency, ambient light strength, and the communication range on our test bed. The hue variation keeps flat for the same color. Spectrum diversity in RainbowRow is reliable. Different from the spectrum diversity, the amplitude is more influenced by the environment. These results show that the amplitude diversity is not as reliable as the spectrum diversity. Nevertheless, due to we only have 4 levels in each diversity, which is a low density, so the amplitude diversity is still robust. Compared with the existing modulation methods, we adopt fewer levels and keeps the considerable symbol distance in each diversity. The combination of this proper symbol distance modulation assists the symbol error rate, SER reduction, compared with the other high-order modulations. Besides, due to the reliability of spectrum and the spatial diversity, it also improves the reliability of weaker amplitude diversity for keeping proper symbol distance. Compared with the 16 color bar and the 32 color bar, RainbowRow achieves a lower symbol error rate in different transmission frequency. As for this throughput, RainbowRow transmits more than the same order modulation, which is a full level, due to its diversity combination. RainbowRow's throughput is higher than 4 color bar and the 4 cask, which use the same level in each diversity. When the frequency is 5 kHz, the RainbowRow can achieve about 40 kpbs throughput. So conclusion. In this work, we explore the spatial diversity in camera imaging process for improving OCC data rate. We combine the spatial diversity with amplitude and spectrum diversity for modulation. Also, we develop a robust and practical OCC system, RainbowRow, and confirm its efficacy. We achieve the symbol error rate less than the 0.05 and achieve the throughput up to 40 kbps at the range of 1 meter. It is a significant improvement than the state of art. This is my talk. Thanks for listening. Any questions?
Okay, thank you very much, Xiao, for the interesting presentation. Are there questions from the attendees? Feel free to use your microphone, camera if you want to, or to use the Q&A box on the websites. Okay. In the meantime, a small question from myself. So you mentioned that you combined several techniques in order to design your solution. So I was wondering, did you use the full toolbox, or are there further optimizations possible? Because I have the impression that you already combine a lot of techniques, and I'm not sure if you could add additional techniques to further improve.
Okay. Oh, I see. So for the spatial, for the amplitude diversity and the spectrum diversity, other research have adopted, and I find the spatial diversity to improve it further. Also, as you mentioned, there actually exist other diversity, and our next work is note the two-dimensional spatial diversity, like a panel. We make the transmitter as a three-dimensional tag, and the different location you can capture the different transmitter. So it is extended from the another spatial diversity. It's a three-dimensional diversity. So we can extend or improve the throughput further. Thanks for your question.
Okay, thank you for your answer. Appreciate it. Let me check if there would be other questions. Just have a look before we then go to the invited talk. Okay, there are no further questions. So thank you very much, Xiao. Appreciate it. Thank you. So let's now move to the invited talk of this session. So it's my pleasure to invite Professor Nirmala Shenoy to take the floor. So while you're sharing your presentation, Professor Shenoy, I will briefly introduce you, if that's fine for you.
That's okay.
Yeah, okay, thank you. So Professor Shenoy received her PhD in computer science and from Germany in network protocols, and she obtained a master in engineering in applied electronics and bachelor's in engineering in electronics and telecommunications from the Madras University in India. She is currently a professor in the Information School in the Golesiano College of Computing and Information Sciences at Rochester Institute of Technology, where she is the director of the Lab for Networking and Security. And her current research projects include wireless and mobile ad hoc networks, future internet architectures, and also the meshed tree protocol. So, dear Professor Shenoy, it's my pleasure to invite you to the floor. Thank you.
Thank you. Thank you. Okay, good afternoon, good morning, good evening. I don't know what timing we are on, but anyway. So this is a project that I have been working with my students, and actually, I apologize, I forgot to include my students' names in this project. And so this was partly funded by NSF and US Ignite in the US. The title of my invited talk was just an expedited internet bypass protocol. I thought I'll preface it with, can we improve internet performance? Because that's what we all seem to be aiming for, okay? And so I stuck it in at the last minute. Any questions relating to this project or its implementation, you're welcome to address it directly to me. My email address is given at the bottom. Okay, so the agenda for my talk today is just a brief a description on the growing internet complexity. And as part of the research that I conducted in this area, I was looking at some of the proprietary solutions to improve performance when you're transmitting data across distances, either using the internet or proprietary solutions that are completely hosted by companies. So I had a quick look into that, and the high infrastructure costs that seem to be invested in these implementation. I'm not proposing that our solution is a solution to all these problems. I'm just highlighting the current internet scenario out there. So when we look at
a small question. I can see your camera, but I don't see the slides, the screen.
I'm sorry.
Maybe it's different for my colleagues.
Got you. I think I know what I messed up. Is it okay now?
Okay. Yeah. Okay. Now I can see the slides.
I'm sorry about that. I'm sorry. So
no problem.
I'll just
Thank
skip
you.
what was there. So this is the agenda, and going through it again, I start with the growing internet complexity and some proprietary solutions. And then we asked this question, when I was working on some NSF project on future internet architecture, that's where this whole work originated. Can we improve the internet performance? And so eventually we did come up with a cost-effective solution. And I'm assuming it is a low complexity solution. Anybody with any opinions, you're more than welcome to get back to me. And that's what I'm going to be talking about today. It is the Expedited Internet Bypass Protocol. So we literally bypass the internet protocol. How did we evaluate this? We not only designed and developed it, but we performance tested this protocol by coding the protocol and evaluating on the Genie testbeds in the United States. It's widely available. I think people overseas can also access these resources. And because we were bypassing the internet and talking about improving the internet performance, we did some performance comparison with similar topologies running the internet protocol and BGP, and the other scenario was internet protocol and OSPF. I'll talk about some future work that can be conducted in this area because I had to limit the current work to whatever funding I had at that time. And then I'll open it up for discussions and questions. So if you look at the growing networks and the networking needs, if you look at the number of internet users and the number of networks, they seem to be continually growing. And currently we have the only protocols supporting this huge infrastructure is the layer 3 protocols, which is the internet protocol, and BGP and OSPF, which are the routing protocols that populate the routing tables that are used by the internet protocol. Are they addressing the growing needs? It would seem that they are doing a pretty good job, but is it just the protocols that are addressing these needs, or are they other technologies like the huge advances that we notice in microchip technologies, transmission technologies? We had a great speaker just before my talk who spoke about improving transmission technologies. So all these have literally contributed to the huge advance that we see in communications today. But if you look at the protocols, these 3 protocols are pretty old and they have been quite stagnant. And they are addressing the current needs because we have a lot of complex overlays and whatnot on top of these protocols, and we seem to be doing pretty good, okay? What are the challenges when we continue using these protocols? They were developed several decades ago and they have severe limitations. And I'm sure all of you will agree with me when I say that they are pretty sluggish and unstable. So let us look at the growing needs now. And this is something I did as part of my research. In fact, when we were funded under US Ignite, we actually did this work as communication support for emergency networks. During an emergency, if I try to send all the emergency data using the internet, that's not going to be reliable. It's not going to be secure, okay? And for those purposes, we developed this protocol, but it has evolved quite a bit after that. So the predominant users that I'm looking for who could use this is federal networks, defense networks, emergency networks. They need secure, reliable, and fast delivery of data, but that does not preclude other users. So if I look at some of the services that are being supported, not only in the internet, but using the internet and with add-on overlays and private networks and so on, are the content delivery networks. So we see these growing CDN providers and network with a heavy infrastructure investment. And you have these big players like Google, Amazon, Facebook, etc. They have come up with their own proprietary solutions, not to mention the private CDNs. So looking at content delivery networks, the need there is you have to route huge amounts of data. We experience this whenever we do a search and things like that on the internet. We are literally downloading huge amounts of data, and this requires networks that have high availability, high speed, reliability, security, you name it, and we need it. And the current solutions, like I mentioned in my previous slide, is costly and redundant infrastructure. I'm not going to go into the rest of this slide because this is just explaining content delivery network and the need for all these high speed, high reliability services. The next slide is one paper that I came across. It was published in ACM SIGCOMM. It is Google's Espresso and how they are trying to use the internet and their private wide area networks to connect data centers. And they have their own proprietary routing protocols, which are modified versions of BGP. And they are using IPGRE and MPLS encapsulation. The point about putting this slide in is the complexity that we are heading towards just because we want to have all these nice performance improvement in our networks. Okay, so the internet today, internet infrastructure is widely deployed, but some of the challenges that typically I looked into is the heavy traffic that we see in the internet, and then we try to prioritize traffic amongst all the traffic that's going on there, the severe security challenges that we faced at layer 3, and the lack of reliability. I was actually sitting in one of the sessions earlier, and I remember he pointed out all these three performance issues that I'm mentioning. BGP, which is still continuing as a routing protocol for the bigger internet out there, has severe scalability issues. And as a professor in networking, one of the things that I emphasize to my students is just look at the complexity at our border gateway routers or border routers or gateway routers, where you're talking about interworking among OSPF, IBGP, eBGP, etc. That is our internet scenario today. So data travels across several networks, several tens of routers. Routing paths are defined through the routing tables, and a quick look at our routing tables tells us that it has exceeded 800K entries. Severe security concerns, I don't have to emphasize that. Consequences are non-deterministic delays, unpredictable loss of data, security attacks, and compromised privacy. What is the solution to all these problems? Can we improve the internet? Well, we have been trying this for quite some time now. Can we replace the internet? I think that is a really daunting challenge. Can we bypass the internet? Well, from whatever we have seen and whatever our solution tells us, that is a possible solution. So what we have come up with is an expedited internet. I call it expedited because the moment you bypass all the traffic at layer 3, you are expediting the traffic that is handled by this particular protocol. And the nice thing about this protocol is you can turn it on when you want it for specific IP end users and turn it off when you do not need it and fall back to the internet protocol and whatever services you're supporting there, okay? So like I said, from whatever results we have achieved with this protocol, and it's a prototype which works along with the internet protocol. We have implemented it in Genie routers and evaluated it. So the expedited internet bypass protocol, you can use it for end-to-end IP packet delivery. When I say end-to-end IP packet delivery, I mean IP networks or IP users. Believe it or not, we use no routing protocols. We are not bothered about disseminating routes at all. And we don't have any routing tables, okay? Auto-configured router addresses at the routers provide the routing information. It not only provides me with routing information, but it provides multiple routing paths. Any topology changes, you have a localized impact. Extremely fast recovery, we could test it out to a maximum of 30 nodes or something, okay, on the Genie testbed. And it was a very fast recovery on component failures. A single protocol is doing both the routing and forwarding for us. It actually integrates both the control and data planes at this point. And as far as I'm concerned, it is a simple and robust protocol. Okay, what is this expedited internet protocol? A very simple picture highlights this. This is the way it runs. It's running below the internet protocol. So this is your IP network, right? So when packets are coming in from the clients, and if you run this bypass protocol in the routers, it will not allow the packet to go to the internet protocol. It bypasses it, it captures it, and then it's completely handled by this bypass protocol that's running below the internet protocol. Just a quick check on my time. Okay, where are we? So how do we do the routing with the EIBP without any routing protocols, no route discovery, no route dissemination, etc.? This protocol routes using structures that are there inherent in the network. These structures can be physical structures, like I'll show you in a minute, or they can be virtually formed structures or virtually defined structures. This makes the protocol scalable and modular. Again, I'm making a few claims here. Some of them I have not really justified it later on, but I know it from the way it works that it is scalable and modular. And it also avoids loop. We go to quite a bit of effort trying to avoid loops in our routing protocols. So this is a network. If you see here, any network and autonomous system, if you take, you have these core routers, you have the distribution routers, and you have the edge routers. This is a very popular network structure, 3-tier structure that we notice in any network. So let us see how to do routing in this network with the structured addresses. And like I mentioned earlier, the addresses carry the routing information. So what we try to do is we associate the core routers with tier 1. They are the tier 1 routers. And all the distribution routers are the tier 2. And the access routers or edge routers are tier 3. So the address allocation is pretty simple. Okay, I need to do address assignment only for the core routers. And I stick in the tier number here. And this is the first router in the core, 1.1, 1.2, 1.3, and you can go on for as many core routers as you have. The distribution routers are connected to the core routers, and the only thing I need to do there is assign a tier value to them. So, and then they get the rest of their address from the core router that they're connected to. So here you see 2.1:1, 2.3:1, derived from 1.3 here, and so on, and the access routers get their own addresses. On any failures, they self-configure and self-heal, okay? That's a very common terminology we come across in wireless ad hoc networks, but this protocol has that capability. Now, this is an animated slide, so I'm just going to quickly walk you through this and show you how an IP packet from an address 10, 11, 22, 33 is delivered to 10, 22, 33, 11, okay? There are 2 different networks here. So when the client forms this IP packet, this is the way it's going to look at. And when it is delivered to the access router and the EIBP protocol is running here, so what happens is when this packet arrives at that router, the EIBP running at that router captures the IP packet, and he looks up the structural address corresponding to this destination IP address, okay, that is connecting to client 2, which at this point is 3322. Though we have multiple addresses, for simplicity, I'm just showing one address here. And then it encapsulates the whole IP packet in its header. And it identifies the next neighbor. The beauty of this type of addressing is using the destination label, I can identify if there is any of my neighbors who is closest to that. Well, if I don't have it, I'm just going to send it to my neighbor who has got more knowledge than me, because I'm a little bit localized and restricted here, okay? So he identifies, in this case, 231 is the closest neighbor to 3322 because they do have a common parent here, which is 1.3. So he sends the encapsulated packet to 231. And when the packet comes there, this router identifies, he has got his neighbor knowledge here. He identifies 232 as the neighbor closest towards the destination 3322. These are two addresses, okay? Because I get 3211 from this distribution router and 3322 from this distribution router. So I have multiple addresses and I have multiple paths. And then what happens? He sends it to router 232. And then router 232 forwards it to router 3211 or 3322. And this router de-encapsulate the IP packet and sends it to the client. And that is a very simple explanation, but much goes on behind the scenes. This slide is a bit too busy. I'm not going to explain it. I just threw it into, I think all of you are going to get a recorded version of this and you'll get my slide set also. This is the comparison chart where you're literally comparing the destination address with my address and my neighbor addresses and making the decisions how to forward. It is a few substring, superstring matches before you forward it. And like I said, if none of my neighbors are closer to the destination, you just send it to my parent because the parent, all the addresses are derived from the parents. This is the EIBP implementation. These are some of the messages we used to implement this protocol. And like I said, it's both a control protocol and a forwarding protocol. So the hello messages, because I have multiple addresses, every router sends out these hello messages with variable addresses. And we are planning on optimizing it to send the content in the hello message will be changed based on the number of address changes I have. If there are no address changes, then I just send a single byte hello message. Now, how did we do this when we implemented it in the routers? We actually used Ethernet frames, okay? And we stuck in a special type value in the Ethernet header. So when the Ethernet frame enters the router, they look at this type value and it is delivered to our EIBP protocol, which takes over the handling of the packet from there on. I'm trying to skip a lot of stuff that is in here. I apologize. Okay. This bypass protocol has been implemented as a software that operates below the Internet Protocol. It was prototype tested for intra-AS operations only till now. This code was written in C language and ported into Ubuntu 16.04 on the Genie testbeds. And the code is available on GitLab. If anybody is interested, we can make it available to you. And there is some information also available, when we demonstrated it first, it was actually for an emergency network. And we had the Monroe community folks attending our presentation at that time. So there is a little bit of story available about this protocol in this link. The code is ported into the routers, and that's what I've been telling you in the Genie testbed. It runs below the Internet Protocol without disrupting normal IP operation. But if you want EIBP to be effective in any network, then all routers in the network must run a copy of EIBP. And this is a repeat from earlier, one of my earlier slides. As and when you need, you turn EIBP for specific and IP networks or hosts. And I've been talking to you about this Genie testbed on which we ran the EIBP, and we compared it with IP running OSPF and IP running BGP. So a little bit of information about the Genie testbed. I'm not going to go through this. Much more about this is available at this site. Okay, so we just reserve resources on the Genie testbed. We port our code onto the routers there, and we then run the protocol. So this is one of the test topologies. More about all the test runs that we did is available in this paper that we have cited here at the bottom. So this is a 17 router topology, and all the red nodes are IP clients. So you can easily send IP packets, and you'll see that all these routers that are running EIBP will take over the IP packet and deliver it to the end nodes. And predominantly, we were trying to test the performance improvement or the performance in case of failures. So in this case, we introduced 3 different failures here. If you notice, we are touching literally the core routers. And when we fail the links, we then assess the performance that we got with the 3 different protocols: IP with OSPF, IP with BGP, and EIBP. So predominantly, like I said, we were focusing on the convergence process, because one of the major challenges that we faced with our internet protocols is whenever there's a topology change or failure, the convergence takes quite some time. And during this time, the packet delivery is not reliable, and your packets can go anywhere they feel like, because the routing tables are highly unstable. So when we talk about convergence, there are 2 timings that are associated with the convergence time. The longer the convergence time, the more impacted is your network performance. The failure detection time and the protocol recovery time. The failure detection time is nothing, it's more a communication between adjacent nodes on how do they identify a failure detection. It really does not reflect on the protocol, but the protocol recovery time is a direct reflection on the protocol itself. And one of the recent works that have been conducted in this area is BFD, which speeds up failure detection. But we did not use BFD in our protocol, but we still got very fast failure detection, and I'll explain why. So this is again a little bit of an overloaded slide. All that I'm trying to tell you here is when we were running the tests, we did not run BFD and BGP. We are planning to do that in the future. So the failure detection itself took quite a bit of time, because it depends on the hello timer and the dead time interval and so on. And also the OSPF took quite some time for failure detection. So I did separate out the failure detection and the protocol recovery time. And recently, based on some research students that I have, we are using BFD and OSPF. We are yet to implement it for BGP. So I'm going to skip this and come to the results that's more important here. So this slide is the performance that we recorded for the failure between N3 and N4, that is the nodes in the topology that I showed you earlier, the failure between N0 and N1, and all these are at the core and distribution level, and N0 and N3. So BGP had some failure detection. We separated that out, and it had 100 seconds of protocol recovery time. When I say protocol recovery, I'm looking at the stabilization of the routing tables at all the routers that are in the network. And when we looked at OSPF, keeping aside the failure detection time, it again took 30 seconds for all the link state databases to stabilize and all the routers for their routing tables to stabilize. And similarly, for the other failures, you see that it is high. Believe it or not, for our protocol, the protocol recovery time was exactly 1 second, because the failure was localized. I didn't have to inform everybody in the network about the change. It was just a localized impact. I had to inform my neighbors, and I'm done, and I recover from the failure, and I use one of the other paths that are immediately available at that router. one link fails, I have the other link readily available. What is this impact ratio? This impact ratio is a very, very important performance which we study when we look at routing protocols, and that is how many routers got impacted whenever a change was made in one of the routers or if there was a failure. So in the first case, out of the 27 routers, 26 routers had a change in the routing table. With OSPF, 8 of them had a change. Whereas in our case, only 2 routers changed any information in the routing tables that they had. Okay, and so forth. The rest of them is available here. FD, by the way, stands for the failure detection, which we have separated out. And I'm looking only at the protocol recovery latency. So these are the routing table sizes. BGP had 93 entries. It had multiple backups, of course. And OSPF had 83 entries. And these are the maximum entries recorded at some of the routers. And it had at least one backup available. Whereas in our case, I'm looking at the maximum neighbor table size because remember, I compare the destination addresses with my neighbors and their addresses, and then I decide on how to forward. So that is the maximum neighbor table size that I'm looking at, and that was 5. So what are the benefits? When I look at the performance comparison that we conducted so far, it is several magnitudes in recovery time on failure. Routing is extremely simplified. A single protocol updates routing information and forwards packets. And because I bypass the internet protocol, I think I can claim that I'm improving on the security and privacy of the data transfers because it's not visible to the majority of the world out there. Okay. Improved fault tolerance, and seamless interworking for intra-AS and inter-AS operations. And that is something which I want to quickly look at. Okay, I had this intra-AS scenario, which is great, fine. I have only 3 tiers, so it works. How about if I want to extend it for inter-AS? If I look at the ISP structure today, the internet service providers, they are beautifully organized into tiers. Actually, during our project, we were working with level 3 at one point in time, and they had a maximum of 7 tiers in their networks. So if I, along the same lines that I allocated the addresses here, if I can allocate addresses to the ISP tiers, I think I can take care of the inter-AS forwarding also, okay? And this is a simple slide. Again, it's a little bit busy. All the information is here. If you want to go across from one customer autonomous system to another customer autonomous system using a transit autonomous system, how will the packet forwarding happen for inter-AS, that is EIBP extended to inter-AS? Unfortunately, I don't think I have much time. So I'm going to stop it here. I'm supposed to stop here, right? So future features that we are looking at is a fast failure detection, and rather than using BFD, because when you implement BFD in any router, it sort of makes it a little bit more complex. You're sort of communicating between your routing protocols and BFD, which is running in the system's engine, okay? So we wanted to avoid that, and some of the concepts like the inter-AS routing and so on is yet to be tested. Future benefits. I think this will be an efficient use of internet infrastructure. We can leverage the current infrastructure to offer superior services, especially if you're talking about emergency network, defense networks, etc. Or we can even reduce the resource-intensive infrastructure that are being deployed with complex solutions. Again, I'm not proposing a solution to all the problems out there. I'm not suggesting that this is going to replace all this complex implementation, but it's a very simple, robust solution that can run below the internet protocol and offer great services. How much time did I take?
Okay. Thank you very much, Professor Shenoy. We highly appreciate your talk. Very interesting. So we slightly exceeded time, but that's fine. We also started a little bit later, so that's no problem. And I would like to invite the attendees to ask one or two questions. So are there questions from the audience? Let me check the Q&A box. Or feel free to use your microphone or your switch on your camera. In the meantime, I also have a question. It's about the evaluation scenario that you presented for evaluating the performance of the EIBP protocol, and you mentioned that you used an emergency scenario, and I was wondering, did you also transmit multimedia content, and was it an interactive application that you demonstrated?
No.
Could you elaborate a little bit on this? Yeah.
No, all that we did in that particular evaluation was that EIBP gives you a significant improvement compared to using internet protocol. That's all.
Okay.
So we just transferred data.
Okay, I see.
So we didn't test out with multimedia and so on. So.
All right. Okay, I see. So you focus on the connectivity.
Just
are there any plans to also in future work or in future projects to also focus on multimedia content and also interactive content maybe?
Oh, we need funding for it. That's the problem. I'm looking for funding and some industry support, because this is a solution that's ready for deployment. It has been tested out. The code is available. It works with internet protocol without impacting any implementations in the internet or anything. So we are looking for some support and funding at this time.
Right. Okay. So maybe colleagues in the audience can provide guidelines or can give advice. That this would be appreciated. Okay, thank you. Are there other questions? Let me have another look at the Q&A box. Or any questions from the participants? No, I don't see any. Okay, I would like to sincerely thank you, Professor Shenoy. We highly appreciate your presentation and your time.
Thank you.
Thank you very much. And we now arrive at the closing of the session. So let me thank all the presenters in this session, and also the presenters in the other sessions. I also would like to thank my colleagues, program committee chairs, for organizing this workshop. So it was a pleasure to work with Cedric, with Xiao, Faten. We were a good team, I believe, to organize this as program chairs. And we also highly appreciated the interaction with the general chairs, Kiran, who is here, but also Kike, Sherman, and Shen. So thank you very much for the nice cooperation that we had. I think it's also important to mention that all videos have been recorded. So all presentations have been recorded during the entire workshop, and they will be available on this website. So if you browse this website later on during the next days, weeks, I believe, but Kiran can correct me, it will be available for several months on this website. So feel free to distribute the links to this program, and also invite others to benefit from the interesting presentations. So with this, I would like to hand over to Kiran, who is the General Chair. So please, Kiran, the floor is yours. Thank you.
Thank you, Professor Turck. You wonderfully executed the final session, and it was pretty inconvenient for everyone working through different time zones. And so I appreciate the effort that came from all the chairs, basically the entire organizing committee. And since you already thanked them, I won't repeat it. So normally when we do workshops, in the end, we try to get the pulse from the room, that what their thoughts are, how they feel about it, and just open the floor for some discussions and brainstorm ideas. Unfortunately, I see that the attendance is pretty low and it may not be possible to have that kind of discussion. But just wanted to summarize that there was a motivation behind this workshop. So when we talk about NIPAA, it is about new class of applications and how we can collect all the ideas together and think of a general common direction for the solution so that things are not fragmented and they come together. And I witnessed some of that in the entire workshop today, starting from the keynote presentation, where there were two key aspects that were highlighted. One, that sometimes technology is ahead of what industry is ready for. For example, active networks, but now it is coming back in the form of P4 or data plane programmability, and maybe going forward there are means to extend those programmability. And this was very well complemented by Torles' talk, where he introduced the notion of contract and how we can solve the multi-layer problems, which again relates to relates to actually Adrian's talk, where he talked about how IP is at the middle of everything and how we can make it more predictable and better. And I really appreciate that he mentioned that research has to be a continuous and ongoing process. So when we do NIPAA kind of workshop, we look at new requirements and challenges, we look at current limitations, and also think about the new solutions. And all the papers that were presented, actually just let me summarize that. In total, we had 10 submissions, and we accepted 8 papers out of it based on the merit. And all those 8 papers were pretty much at the same level. So for us, it was very difficult to filter out another 4 papers among those 8 papers. And you must have observed from those talks that all those 8 papers were very relevant, and they were novel ideas and perfectly suitable for this workshop. So what are we trying to do? I hope we can continue to have discussion going forward, and we'll see you next year again to see what kind of progress you have made in your field. And I highly encourage that we talk to each other and find out more about each other's research. For example, I know I'm going to reach out to 2-3 authors and talk to them, hey, how can you do more in this area? I have this problem, can you solve it for me? So I hope we continue to have this conversation, and many thanks to everyone for joining it. Thank you. That's it, Professor Turck. We could probably close the workshop now. Francesco will let you take over the controls, please.
Okay, so in case I will close the meeting.
Thank you, Francesco, for all your help and support.
Thank you also for the interesting workshop.
Bye-bye, everyone.
Bye. Thanks.